Hey guys, David the physics tutor over here at GCC, and I wanted to make this video to showcase a very simple but effective method in analyzing DC circuits called the mesh current method. And in part one of this video, I'm going to be showing you the long way of doing this and really breaking it down step by step, pretending it's almost your first time analyzing a circuit. And in step two, I'm going to be showcasing the shorter way where you can just jump to your final set of equations, plug it into your calculator, and let your TI-84 do all the work for you, assuming you're allowed to use a TI-84. So what does the mesh current method use? Well, we're still using all of Kirchhoff's law, right? Kirchhoff's voltage law tells us that all the voltages in a closed loop are going to sum to zero. And his current law tells us that all the currents in a junction sum to zero, or I think more intuitively, the current going into a junction is going to be equal to the current leaving a junction, or I in equals I out. And since we're only dealing with batteries and resistors, we still need to know Ohm's law, which is voltage equals current times resistance. And so let's get into it. In step one, mesh current method tells us to assume a direction for our current. So I'm going to assume current is going clockwise. I'm going to notate this as I1. Our second loop here, I'm going to assume clockwise. Since I already assumed clockwise for one, might as well assume clockwise for the rest. There's no reason to get all fancy smanchy and start picking different directions wherever we want. I'm going to call this I2. And you might be sitting there and you're going to say, David, don't we already have a problem with step one? Because you have I1 going this way and we have I2 going that way. So we don't know what the current going through R2 is, whether it's going upwards or downwards. And I would say, wow, you are extremely observant. Good job. And yes, there is a solution for that problem. So remember, we assume directions here, so it's important to stay consistent with our assumptions. So at this point in our circuit, I1 would be leaving this junction, right? And junction is just a point where the currents are all entering and leaving. So there's I1, and then I assumed I2 is going into this junction. Now I3, I don't know, right? I3 can be going downwards or it can be going upwards. It's truly up to you on what you decide. You're going to get the same answer regardless, but you're going to get a different sign. So what do I mean by that? So I mean that if I assume that I3 is going downwards, like let's just say I picked this as my assumption, I assume I3 is going downwards. That would have to mean that once I get my final answer, if I get a positive answer, I was correct. I3 is going downwards. If I3 is a negative answer, it just means I assumed the wrong direction. It means I3 is going upwards. And the same could be said for I1 and I2. A positive I1 means current's going clockwise. A negative I1 means the current is actually going counterclockwise. That's all that means. And now this is where we use Kirchhoff's current law, right? The current going into a junction is equal to the current leaving a junction. So I have these two currents entering my junction, then I have I1 leaving my junction. Right, so let's set up this formula. So I'm going to say this is my I3 formula, and I'm saying that the currents entering my junction, I3, or the sum of the currents entering my junction, I3 plus I2, are going to be equal to I1, the current leaving the junction. Again, right there, we just use KCL. So it's important to remember we made that assumption there. But I just wanted to address that right away. Now let's get back into our mesh current method. So step one was to draw our loops and assume a direction. Step two is to analyze each loop individually. And I'm going to pretend to be a little electron on the path that I set out for myself. So I assume I'm going clockwise. So I'm following my little path and I hit R1 here. And since we know potential goes from high to low, I can just assume that this was the positive end and the negative end. Remember, resistors aren't polarized, so it actually doesn't matter when you're dealing with the actual hardware, but in this analysis, I'm just going to assume that the higher potential is on the left side of R1. So, and then I hit the positive, so I'm going to say positive VR1. I'm following my little path. Now I hit R2. I'm going to say plus VR2. Now I'm following my little path, and this time I hit a battery. So this does matter whether I hit the plus or minus first. Here I hit the minus first, so if I see a negative, I'm going to write a negative. So that's going to be a minus V1. Right? If I hit the positive end first, I would have put a plus V1. So yes, it does matter whether you hit the plus or minus first. And now I'm back to where I started. And since Kirchhoff's voltage law tells us all of these voltages are going to sum up to zero, right? But we know the formula for voltage dropped across a resistor, right? It's just Ohm's law. It's current times resistance. And we know all the resistance values. So I know what R1 is. R1 is just going to be 3. And the only current going through R1 is I1. So it's going to be 3I1 plus. Now this one's a little bit trickier, right? Because like we said earlier, we have current going this way and current going this way. And we're not going to just put I3 there. What we're going to do, we're going to say 4 for the resistance value. And since I'm analyzing loop 1, I'm going to assume that I1 is the positive direction. So what's going to happen here? I'm going to say I1 minus I2, right? And that's because I2 is going in the opposite direction. Therefore, it should have the opposite sign. So I1 minus I2. If you did it backwards, I2 minus I1, you will 100% get the wrong answer. And minus V1, well, V1 is just a battery. And so that's just a constant value. We hit the minus, so it's minus 6 is equal to 0. And now we can just do some simplification here, right? Combine like terms. 3I1 plus 4I1 is going to be 7I1 minus 4I2. And we can put all the constants on the right-hand side. And that is our I1 equation, right? And that was our analysis for I1. Now we're going to do the same thing, but for I2. So I'm going to pause the video and erase my markings, but I encourage you to pause the video and try to do it on your own. So hopefully you tried this and you're skipping ahead, but again, I'm still going to go through it. So I'm going to be my little electron on my little path, and I hit R2, and I'm going to annotate that I'm analyzing loop 2 here. This is going to be a voltage dropped across resistor 2, and I'm going. Now I hit R3 plus VR3. I'm going. I hit the positive part of our battery first. And again, since I hit the positive first, I see a positive, I write a positive. That's going to be a plus. V2 is equal to 0. Hopefully you didn't even write this part and you just jumped to the second step of doing this, but that's okay. All right, I'm knowing this is equal to 0 because I'm back to where I started without crossing any other elements. And now let's plug in our formulas. So voltage dropped across the resistor is just Ohm's law. And VR2, again, we have that issue where we have current going upwards, or sorry, downwards and current going upwards. This time, since we're analyzing current 2 or I2, I'm going to assume that I2 is the positive direction. So I know this is going to be 4 I2 minus I1, right? Because I2 is going in the positive direction and I1 is going in the opposite direction. Therefore, it should have the opposite sign. So I2 minus I1 plus VR3, we know the resistance value, which is 4 times I2. And V2, again, is just a battery, so that's just a constant value, plus 2, which is equal to 0. And now let's just do some math. This is going to be a 4I2 plus 4I2. This is going to be a negative 4I1 plus an 8I2 is equal to negative 2, right? So all I did there was just combine like terms and put I1 first and I2 second. And this is going to be my I2 equation. From this point forward, we're just going to be using math. There's no more physics involved. So I'm going to pause the video and just rewrite my equations so that way it doesn't get too confusing. But we're just going to do some math to find I1 and I2. And after we find I1 and I2, we're going to plug it into this top equation and find I3. So hopefully you just skipped in the rest and just checking your final answer. But again, I'm still going to do the math, pretend that, and walk you through it. So again, all I did here was just rewrite those highlighted equations. Now let's do some math, right? So here we can simply use elimination, right? I can multiply this by 2. And this is going to become 14I1 minus 8I2 is equal to 12. Now I can just combine my equations and I get 10I1. The I2s are going to disappear. And this is going to be equal to 10. Right, so then I know that I1 is going to be equal to 1 amp. Now I can just plug this into either my I1 or I2 equation. It really doesn't matter. I guess I'll plug it into the first one just because. This is going to be 7 times 1 minus 4I2 is going to be equal to 6, right? And it says to be negative 4I2. 6 minus 7 is going to be negative 1. I2 is going to be equal to 1/4, which is going to be equal to 0.25 amps. And again, all I'm doing is math right now. Then to find I3, I need to use this equation. So let me bring that down as well. Like I said, all I'm doing here is math. I now know I1 and I2. I just want to know I3. So I can rearrange this equation as I3 is equal to I1 minus I2. And I1 is simply 1 minus 0.25. So I3 is equal to 0.75 amps. And one thing to note here, notice how we get positive answers for every single current. So what does that mean? That just means we assume the right directions. And it's not drawn on here, but remember that when we assumed our I3 direction, we assumed it was going downwards like this. So we got all positive answers. That means we made the right assumptions. It doesn't matter whether you made the right assumption or not. If you get a negative answer, it just means it's going the opposite direction. But what does the question ask us for? It asks us to find the current going through R1, R2, and R3. So let me recopy this picture and bring it down so it's a little bit simpler to understand. Okay, sorry. So I kind of reorganized things a little bit. That way we could see it. Remember, so it says find the current going through R1, R2, and R3. I'm trying to get it to fit all in the same image. 1 second. Apologies about that. All right, here we go. So it says find the current going through R1, R2, and R3. So let's be able to, I guess, predict these answers. Well, the current going through R1 is just going to be equal to I1, right? Since that's the only current going through that resistor. And the current going through R2 is going to be equal to I3, right? And then the current going through R3 is going to be equal to I2. And now when we write these final answers, I going through R1 would be equal to 1 amp. I going through R2 would be I3, which is just 0.75 amps. And I going through R3 is I2, and I should write this equal sign a little bit neater, is equal to 0.25 amps, right? And this would be our final answer, right? And you would want to make sure you have your picture notated because your professor is going to be able to know which way is your positive and negative direction. But again, this was the long way of doing this. And in part 2, I'm going to show you how to just jump to your final set of equations and plug it in from there. So I'll see you in the next one.